Good morning and welcome to this month's webinar on pipe stress analysis. Thank you very much for joining us today. We have two of our experts on the line, Brandon Grodi and Chris Mach, that'll walk you through the webinar. And if you have questions along the way, please submit them through the Q&A feature on the website. Thank you very much, and I'll turn it over to Brandon.
Well, hello. Welcome to our webinar. Chris, if you don't mind advancing the slide, please. So as that slide comes up, I'll introduce myself. I'm Brandon Grodi. A little bit about myself. I'm a PE in multiple states, as you can see. I've got my BSME from the University of Toledo. I've got about 15 years of consulting experience. I started out in piping design. I transferred over to pipe stress probably about the middle of that 15 years. And if you're familiar with pipe stress at all, you might find it a little entertaining that I've got a past with Al Gore. It's a very interesting program, but we've since upgraded to Caesar 2 and AutoPipe. So my current title, I'm the mechanical department manager here at Matrix. Next slide, please. So our agenda for today, obviously you're here to learn about pipe stress analysis. First, I'm going to take you through who Matrix Technologies is, a little bit about what we do, and then we'll get into the meat of the webinar. First, what's the goal of pipe stress analysis? Next, what is pipe stress analysis? And then, when is it required? When is it recommended? There's a difference there. The code can be vague at times, so we'll try and help you understand that a little bit better. Then we'll take you through a case study. Chris has got a very nice example of a simple pipe system, but I think it highlights some of the evils of pipe stress analysis well. And then finally, what's the value of pipe stress analysis? So that can be a little bit tricky. There's short-term value, there's long-term value, and sometimes it's hard to connect the dots. You may see something in a refinery setting, for example, that you may see excessive pump vibration, for example. It's not always intuitive that pipe stress can lead to excessive pump vibration, but it's a very real possibility. So I know there's some PEs in the group. If you've requested that PDH, that'll be available within the next 72 hours. If you do have any questions, please use the chat feature. I think it's titled Q&A in Teams Live. Our questions will be addressed at the end of the webinar. So, as promised, a little bit about Matrix Technologies, who we are. 40 years, we're celebrating our 40th anniversary this year. So it's a big accomplishment for us. 300 employees, 65 million in annual revenue, and projects completed pretty much all over the world. Now we do focus domestically here in the United States, but some of our clients have taken us abroad into continuing projects, and that's, we followed them outside of the USA for that. One of the big stats that we're very proud of is this 85% additional engagements with satisfied customers. That tells us that what we're doing is helping our customers meet their needs. It's satisfying their needs. So that's one that we really pride ourselves in. A little bit about our geography. So we've got 7 offices. Maumee is our headquarters. That's near Toledo, Ohio. That's where I'm coming to you from today. Chris is in our Cincinnati office today. We've also have offices in Minneapolis, Indianapolis, Kansas City, Denver, and our newest office just opened up about a month ago in Atlanta. A little bit about the industries that we serve. So, pipe stress analysis, it's primarily focused in oil and gas, chemical, and steam, anywhere you see steam. So food and beverage, wine and spirits, that type of thing. A little bit of pharmaceutical and biotech. But just to give you a glance at who we are, we also service packaged goods, metals, aggregates. Next slide, please, Chris. Thank you. So our services, industrial automation and information systems experts. We also have an MES group. Our focus, mine and Chris's, obviously we're in the mechanical department here, is process, facility, and machine design engineering. It's very broad, and I'll hit on that in one of the next slides here. And then we also offer EPC services for turnkey installations. It seems like the world has shifted a little bit towards EPC services. I think it's easier to manage the contracts from the owner's perspective. So we've made an investment over the last 10 years, and we've really gotten into the EPC services. Again, we're a full service engineering company, and I want to touch on safety. So safety is one of our biggest focuses. It's not just personal safety. It's not just safety on site. It's safety within our designs. So pretty much everything we do is tied to a code or a standard or an industry standard. And then when we're on site, we're going to follow our customer standards as well. We're going to keep ourselves safe. We're going to keep our customers safe. We're going to make sure that we don't affect operations in any way. So I just wanted to put it out there that the safety is definitely our most important focus in both designs and how we carry ourselves. All right, so this slide, you may need to zoom in. It can be a bit of an eye chart, and I'm definitely not going to go through all of the services that we offer here at Matrix. But what I wanted to do is highlight kind of the breadth of what we do offer. So everything from process control and automation through process design, that's process engineering, piping. Obviously, we'll get into system stress analysis, but even machine design, equipment specs, facilities from basically underground up, and then into project management and construction management, project support. So everything you see on the screen, we do in-house. We have experts in each and every one of these areas, and I've highlighted here on the screen system stress analysis just to let you know that that's what we're going to be focusing on here today. So again, I've touched on it, but multidiscipline engineering experts. We've got over 40 years of experience in engineering services, civil, structural, architectural, mechanical, and machine design. Obviously, those can be very, very different from each other. Today, we're focusing on piping design and pipe stress analysis. Machine design is a very different beast, but we also have those services in-house. Process designs, heavy in the chemical and petrochemical industries with our process designs, and then full service electrical. So that would be power, instrumentation, controls. All of those services we do offer. Slide, please. So focusing a little bit on our mechanical group and what we offer. Process design services, I touched on it a little bit, but we utilize HYSYS in-house. We can do process simulations. We do a lot of OEM equipment integration. So, for example, a lot of times we don't design a heat exchanger, although we can with the HYSYS program. We'll work with a vendor. We'll specify that heat exchanger, work with the vendor, and integrate it into a system. We do a lot of that specification, as you'll see here in this list. A lot of OEM equipment, tanks, pumps, reactors, heat exchangers, full distillation units, really. Batching, storage, loading and unloading systems for both truck and rail. Diving a little bit deeper, process piping. So that's what we're here to talk about today. We've got experts in material selection, obviously detailed design, since that's what we're going to be talking about. We do pretty much everything in 3D these days. Every once in a while we'll see a 2D layout that just makes sense, but typically we model everything in a piping program. We'll use a different modeling program to analyze the stresses, which Chris will get into. But pretty much all of our layouts are done in 3D these days. Obviously stress analysis, retrofit expertise. So, a lot of the units that we're in, a lot of the industries that we're in, they've been established. They've been around quite a while. So a new project might be changing up something in that system. That can present quite a challenge, especially on the stress side. I don't know if the code has changed much over the years, but maybe it wasn't paid attention to much previously, 50, 60 years ago. A lot of times we'll find ourselves in a sticky situation where we're touching an old system, yet we need to bring it up to code, so that can present its challenges. Just a couple other things here: isometrics, spool sheets, all the details for piping designs, we can handle those as well. And again, system stress analysis, so that's what we're here to talk about today. Chris and his team, comprehensive modeling and simulation. External forces, we'll talk about wind, seismic, full spectrum load, vibration. Again, we talked about pump vibration at the beginning of the webinar. That can be detrimental to a system, and sometimes it's related to pipe stress. Expansion loop designs, obviously, to eliminate those stresses. And just a couple notes here on some of the softwares that we use. Typically, it's Bentley AutoPipe that we use. We do offer Caesar 2 every once in a while, but we've got a good working relationship with AutoPipe at the moment. Just a slide here showing some of the different softwares that we use, our engineering partners. So I've talked about HYSYS. HYSYS is a very powerful process simulation program. On the pipe stress side, Chris will get into some of these, but Nozzle Pro from the Pollen Research Group, very, very, I don't want to call it simple, but it's a very useful and very easy to use program. FE Pipe, Nozzle Pro, it's a FEA simulation basically, which allows us to do very detailed analysis very quickly. I mentioned AutoPipe. We use AutoPipe, and then for our FEA, ANSYS Fluent. A very, very powerful program there. And we won't get into it today, but we also offer pressure vessel designs. Typically, we'll use Compress for those pressure vessel designs. So I'd like to take a moment now to introduce Chris Mach. Chris is PE in Ohio and Michigan. He has his Master of Science Engineering from UK. He's been at Matrix probably about 7 years now. I didn't check his record, but seems like about 7 years. He's got 20 years in consulting, however. Focused mostly in pipe stress, pressure vessel design, FEA, CFD, with a heavy focus in refining and chemical. Chris's title is Senior Consultant with the Analytical Services Group. And with that, Chris, I'll let you take it away.
All right. Well, good morning, everyone. Let me advance this slide here. Okay, so pipe stress analysis. What's the goal of pipe stress analysis? And ultimately, in simple terms, we want to avoid these situations. Bent pipe, broken supports, leaking flanges, damaged equipment. And I don't know what's going on with this big tangle here, but I'm pretty sure something's not right. So we'll lump that in with the rest. So, but before we dive in, let's take a step back here before we dive in real deep into pipe stress, because a lot of people have this question about fluid categories. So I want to touch on that real quick. When you get into the pipe stress code, you've got the normal everyday fluid service, which you'll see kind of here at the end of the list. But you've also got category D fluid service, category M fluid service. So I just kind of want to touch on them real quick, because we get a lot of questions about that and the differences. So in pipe stress, especially now, I'm kind of speaking more toward process piping, the 313 ASME code. Category D is your non-flammable, relatively low pressure. It's not very hot, so the quality is a little more relaxed. You still do weld inspections, but they can be visual. You can do different kinds of miter cuts. You can do brazing and soldering. But, it's a little less stringent category of fluid service. Now, total opposite end of the spectrum is your category M. This is highly toxic, immediately dangerous to life and health. And so there's a lot of, it can be flammable as well as being toxic. So there's a higher level of weld inspection, higher quality valves are required, different flange categories are required. So that's the difference between those two. There's also a couple of other categories. You've got elevated temperature, and you get past 800 degrees, you may have to account for piping in the creep range. You're going to have to reduce your welding joint strengths. Elevated pressure fluid service. Now, this is an interesting one because this design it's designated as any pressure that's in excess of a 2,500 pound flange rating. And if you look at that, that's a pressure rating of about 6,100 psi. So when they say elevated pressure, they are not messing around. High purity, anybody that's worked with hygienic piping, you'll have a real good idea of what high purity fluid service is. Basically, you got special welding procedures so you don't have slag in the pipe. You're going to have special valves so that clean in place processes don't leave any fluid and hold up in the system. And then you've got normal fluid service. That's everything else. So, like Brandon mentioned, we try to do everything to a code, some kind of standard, because that's kind of that's like our pathway. That's covers, helps us cover all the bases, make sure we don't leave anything out. Now, there's a lot of different codes for piping, power, process, liquid pipelines, gas pipelines, refrigeration, nuclear piping. And today we're going to kind of focus on process piping, B313. This is typically what you're going to see in a refinery or a chemical plant. Even in like a distillery or a food process, the steam piping that's in a food process or distillery is going to fall under B313. B311 power piping you may see right around the boiler, but once you get out into the plant, it's going to be B313. So, all right, back to what is pipe stress analysis. So, pipe stress analysis, we're going to use to predict the stress in the pipe, loads on equipment, how does the way the pipe and the pipe contents affect things, pressure, thermal growth, thermal gradients, external loads like wind and seismic, transients like water hammer or release from a pressure relief valve, vibration. Brandon mentioned that a little bit. You can have vibration on rotating equipment, or just certain flows, two-phase flow in a pipe will cause vibration. Cyclic loading and fatigue, reduced ductility if you've got really cold piping, even bolt-up strain. Pipe stress is going to help us to predict these loads and predict when they will be a problem. Now, if you look at the code is a little vague. It says, piping systems shall have sufficient flexibility to prevent thermal expansion and contraction or movements of piping supports and terminals from causing failure pipe, leakage of joints, or detrimental stresses in piping or connected equipment. So back to that very first sheet, you don't want bent pipes, you don't want broken supports, you don't want leaking flanges, and you don't want damaged equipment. So that's basically what 313 is saying. So when is pipe stress analysis required? Now, I'm kind of using a standard refinery chemical plant type of definition because it tends to be a little more complete. Now, if you're in a food plant or you're in a process where you have mostly steam, you might not have some of these pieces of equipment. But what we're going to look at here is, formal analysis as opposed to, say, an engineering analysis. And it's really about risk. And if you look at some of these pieces of equipment here, you're going to have fired heaters, steam generators, process lines to and from centrifugal compressors and blowers, steam lines to and from turbines, any kind of a line going to a reactor or a centrifuge. lines to pumps and compressors that are handling hazardous or flammable fluids. And formal analysis is going to be, you know, this, you're going to put it into the software, you're going to look at all aspects of the system, flanges, connections, thermal growth of equipment. Because these are sensitive pieces of equipment, they're high risk items. Not only if you damage the equipment, but if you have a leak with these flammable or hazardous fluids, there's going to be a problem. So there's a high level of care implied. Now, if we go over to engineering analysis, this means essentially the most expedient method that still gives the engineer adequate proof the piping meets codes. Let me tell you, after 20 years of running pipe stress analysis, you know, anything but the simplest run of pipe, we're going to put into that piece of software because it's simpler. It gives you a very comprehensive view of what's going on once you run the analysis. So, you know, we're going to treat these pretty much the same, but let's look at some of these pieces of equipment here. You've got any line greater than 4 inch going to an air cooler. Hydrocarbon pumps not requiring formal analysis. Lines that can't be disconnected from steam out or purge cleaning. Relief systems, closed and relieving to atmosphere both. Lines to and from reciprocating pumps. External pressure due to vacuum or jacketing. Any line greater than 3 inch subject to significant differential settlement or movement of a tank or vessel. You know, if you got a line running up the side of a vessel and you've got a very hot pressure vessel, you can get quite a bit of movement as that pressure vessel heats up. Line subject to vibration due to mixed phase flow. Non-metallic piping. Jacketed or double wall piping where there's a big difference in temperature. And in general, hot piping, and it kind of varies based on the size. You'll see here 2 inch and greater if it's greater than 500 degrees, or, you know, as you get bigger, 12 inch if it's greater than 200 degrees, or 20 inch, all temperatures. And that's typically what you'll see in these refinery and these chemical plant requirements and codes. And for the most part, we will follow that. So, pipe stress analysis tools. We typically use AutoPipe. We have Caesar. They're both very similar in the end as to what they do. They kind of come out from different directions, but B31.1, B31.3 pipe stress analysis. We run an AutoPipe. We can put in different support types, spring cans, expansion joints. Refractory lining can be evaluated. We can look at forces, displacements, wind and seismic loads, anywhere from a simple model to something that's relatively complex. We can put right in here and run and look at the stresses and look at the loads. Now, we don't use exclusively AutoPipe. There's a lot of pieces of code where we might use a separate Excel worksheet. And a lot of these things like an API 650 tank, the API code for centrifugal pumps, which you see part of the worksheet here. What these have is, you know, they're relatively simple calcs that correlate a nozzle size to a given allowable. So we work those out in a worksheet that gives us a feel for, you know, hey, this pump's got too high of a load, but it also lets us then look at the individual loads on those nozzles and try to pinpoint what the root cause of that stress is. And you see we've got spreadsheets for air coolers. We can look at flanges in greater detail, pumps, centrifugal compressors, turbines. All of those we've developed worksheets for to kind of help us keep track of those allowables, how the allowables calculated, kind of what's going on with those pieces of equipment. Now, Brandon mentioned Nozzle Pro from Pollen Research, which is a nice piece of software. What this allows us to do is model the nozzle connection on a pressure vessel or a tank and look at the local stresses. And the other thing it allows us to do is kind of get the flexibility. Now, when you're in AutoPipe, the piping connects to basically an anchor, but it's not infinitely stiff. The wall of the pipe has a little bit of flexibility. It has a little bit of a spring rate to it. So we try to take that into account so that the forces that we're predicting at those nozzle interfaces are as accurate as possible. Sometimes the configuration is, unique. The limitation of Nozzle Pro is only certain geometries can be put into Nozzle Pro. It's kind of a predefined geometry tool. Sometimes you get something like this connection here where you have a pipe going into the back of a large elbow. This was a nice one because it's not only is it very large pipe, but it was also refractory lined. So for something like this, we'll use our FEA tools. We'll go into ANSYS, we'll model the geometry, we'll add the refractory, and then we'll take a look at loads, what's the stiffness of this connection, and then we can take a look at the local stresses and really get a good idea of what will happen in the field. Now, coincidentally, this FEA is the same tool we'll use for fitness for service. You see a pipe or a nozzle with a dent, it's bent, local thinning, cracks, a number of things, and with fitness for service, using the same FEA tool, we can answer the question, is the damaged vessel or pipe still fit for service? And if not, does it need to be derated? Can it be repaired? And we can look at some of those instances. So remember before we talked about, kind of every client has a different recommendation. Well, we would like for you, look at these types of situations. And we, for the most part, we will discuss this with the client when we start, and a lot of the recommendations are similar to what we would do in-house. But there's a few extra things. We tend to be a little more stringent because we've seen what pipe overstress can do and kind of where the cracks in the recommendations are. So in addition to the general recommendations, we tend to follow these additional requirements. Lines going to rotating or reciprocating equipment. Usually if it's greater than 2 inches, we will take a look at it. Lines to fired heaters, steam generators, or boilers above 2 inches. Again, we'll take a look at that. And that's because of the temperature and the thermal growth of the equipment, both. Lines 2 inches and greater going to vessels that are above 250 degrees, because again, the thermal growth of the vessel can play a significant part in that pipe stress as that nozzle moves. Now, the other thing we take a look at is lines connected to API 650 tanks in the lower 10% of the wall. Now, what's interesting about an API 650 tank is you get a little bit of what I would call an elephant's foot at the bottom. And you can see here in the picture, a little bit of a bend. In this case, I believe the tank that we modeled here was about 100 foot in diameter, 40 feet tall. And you can see how the bottom of the tank kind of bulges outward. And depending on the placement of the nozzle from the bottom, it has a little bit of a tilt to it. And the instinct when you're coming off the tank is to put a support right there, right off the nozzle to support things so that, you're not putting any extra stress on this tank wall. And, when you've got that situation, you've got that 1/4 to 3/8 inch displacement, you've got a degree of downward tilt, putting a support right off that tank nozzle can be about the worst place you can put it. What we've done this is a plot, and you probably can't see these down here, but the red is deflection, and each of these points is in 6-inch increments from the bottom of the tank. Blue is rotation. We recommend looking at any connection in the bottom 10%. As you can see, the deflection kind of levels off and the rotation kind of levels off. This point here is with this 40-foot tank is at the 4-foot point, so 10% up. And you can see, you start out at just past 1 degree downward tilt as you're low on the tank, up to just about a 0.1 degree upward tilt, and about a 1/4 to 3/8 inch outward deflection. Now this is going to change with the diameter, the height of the wall thickness, which, all of these things play into it. And, often we'll get asked, well, we see this, and okay, that kind of makes sense, but why don't we see that in a pressure vessel? And, the difference is kind of one of scale. This tank is 100 feet in diameter, is 40 feet tall, and the relative thickness of the plate required to hold the fluid is thinner than, say, for a pressure vessel that's, say, only 5 or 10 feet in diameter, that may hold 50 or 100 psi. So you've still got that same deflection, but in the pressure vessel, that deflection is very small. As just in the API 650, the scale is such that you can see, in some cases, you can see it. Sometimes you can't with the smaller tanks, but when you've got all the piping attached and everything gets heated up, you can definitely tell that difference. So that's one of the things we look out for. And as a little aside, here's some of our recommendations for connecting to these larger tanks. We don't put that first support too close to the tank. We want to give a little room for flexibility. We try to incorporate a change in direction if possible. When we can, locate the nozzle 9 degrees from where the pipe needs to run. Again, so that when you get that little bit of a tilt, either down or up, depending on how you're placed, you've got a little flexibility there. And absolutely, settlement with these big tanks is always an issue, so we try to account for tank settlement whenever we can. But let's look at our case study. Let's look at an example. And so what we're going to do is we're going to try to look at this, and we're going to look kind of a high level, kind of a generic, and then we're going to get down into more specifics. And I kind of want to show you how the stress, how we look at the system changes. And what I want you to think about is sensitivity. What is your more sensitive pieces of equipment? So if you look at this simple piping system, we're going to assume that the piping isn't anchored to any vessel or equipment. It's just an anchor, okay? Let's say it's anchored to a wall. 6-inch pipe, about 290 psi, just shy of 350 degrees. Typically, this wouldn't even qualify for a lot of cases to be analyzed. It's not hot enough. There's nothing special about the anchors. And if we go through and we analyze this, yeah, the stress is a little high. Your thermal stress is about 83% of code, but it's not overstressed. So at first glance, this initial guidance, well, it's not hot enough, it's not attached to anything weird. That initial guidance kind of proves out, okay, it's not that big a deal. But let's dig a little deeper here, okay? So let's look now, this anchor up on the left-hand side, well, it's actually attached to a vessel. So there's a little bit of thermal movement. Remember I talked to, as you get a hot vessel, you get some movement. So here you've got some vertical movement as well as a little bit of radial growth. Everything else is the same. We're going to assume that the anchors on the right are still pretty generic, but then the anchors on the left, this is a vessel. All right. So The stress, because you've got that movement in the nozzle, now your thermal stress changes just a little bit. See, it's hard to see, I'm sorry, it's a little small, but you've gone from 83% stress to say about 105, 106% stress. Not the end of the world, but there's that little bit of increase because, one, you've got the thermal movement. That's really what's affecting the pipe. But also, when you look at the nozzle itself, you'll see that the nozzle is a little overstressed as well. You'll see some numbers here, 150, 200%. So there's some overstress in the vessel nozzle itself. Right, now let's look at, you've got the vessel nozzle on the left. Well, let's look at on the right, these two anchors that we were saying, well, they're generic. What if these are actually connected to a pump? Now, centrifugal pumps are governed by API code. They've got a certain allowable. So let's look at this again. Now, we're not really changing anything on the piping side. We're not really changing anything for the nozzle. But when we assume that these two anchors on the right are connected to a pump, you'll see here, and again, it's a little hard to see, I'm sorry for that. You'll see that there's some overstresses on these pump nozzles. So what I did was I plotted this out because I kind of wanted to show this red line is 100% of piping code allowable. So you see down here on the left, you've got your piping without any thermal movements from the vessels. You've got your piping with a little bit of nozzle displacement on that pressure vessel, okay? So you've got a very slight increase, and then you've got the vessel nozzle itself. And you've got the pump nozzles. So what I'm trying to show here is relative sensitivity. And let's take it even a little step further. Flanges we will typically see fall in this range to the left here, and over toward the right, tank nozzles. And what you can kind of see is a spectrum. In a lot of cases, it's not the piping itself. Sometimes the piping is overstressed, but in a lot of cases, what you'll see is the flanges are more sensitive, nozzle connections are more sensitive, connections to tank, and especially any kind of reciprocating or rotating equipment. These tend to kind of take the brunt of the force. The pipe itself is pretty robust. It's the rotating equipment, it's the places where the pipe is pushing up against, and especially if it's rotating, these tend to be a lot more sensitive. So what is the value of pipe stress? Short term, honestly, one of the things we see a lot is, and a lot of times the first sign there's an overstress in a system is poor rotating equipment performance, a lot of maintenance, a lot of wear. And this is a sign that there's a loading on this nozzle that's too high. Because if you think about it, you look at these pump casings, you go, there's no way that 400 or 500 pounds is going to break this pump casing. But it's not, you're not going to damage the casing, but what you're really concerned with on rotating equipment is those sub-thousandths of an inch clearances. So once you put that load on the casing and the pump casing distorts, then you start to see wear, you start to see rotating equipment maintenance damage. You'll see alignment issues as well. Flange leakage, a little less common, but that definitely happens. Bent vessel nozzles, that's always a no-no. Long-term payback, improved pump maintenance, no fatigue issues, more resilience to seismic and wind type failures, less failures from pressure vessel release, PSV release events. Now, I firmly believe that every story should conclude with a happy ending. So I kind of wanted to give you a quick view of how we fixed this particular line. We put in a little bit of a loop to let things flex. We added a spring can to take some of the load off the pumps, and we got this system back in working order. And last I heard, it was working with no maintenance issues. So I always like to end with a good note. So a little recap of what we've gone through today. Matrix Technologies, full service engineering provider. Okay. Pipe stress analysis. Okay, what's the goal? We want to avoid unsafe conditions. We want to avoid anything that would be detrimental to our system integrity. What is pipe stress analysis? It's a code-driven method to ensure safe design for the pipe and for the equipment. What is it required? Sufficient flexibility to prevent failure, leakage, detrimental stress, distortion. Knowing when to apply pipe stress is a little bit of an art form, but hopefully we've shown you some areas of sensitivity today. So when is pipe stress analysis recommended? High temperatures, API 650 tanks, equipment nozzles, especially rotating equipment, long runs, large bore piping. That's kind of your key points. What's the value of pipe stress analysis? Safe system design, pump operability, any kind of rotating equipment really. Long-term fatigue, wind, seismic, upset conditions, just an overall a safe and robust system. So, questions?
Okay, Chris, we do have a couple of questions that have come through. The first one actually, I think, is fairly simple. Can we get copies of the slides after the presentation?
We should be able to.
Very easy one. The next one is, oops, I actually published the wrong one. So this one, can a lot of pipe stress be alleviated with welding designs and situations? What's the question?
Okay, repeat that for me again.
Can pipe stress be alleviated with welding designs and situations?
Yeah, if I'm understanding the question correctly, there's a number of ways you can alleviate a pipe stress. You can use an expansion joint. You can use a spring can. I'm a big fan of using the inherent flexibility of the pipe. So you'll see in some cases pipe loops, or sometimes like what they'll call a Z-bend, an offset. So there's a number of different ways. It depends on the situation. If it's a long run of pipe and it's a fairly high temperature, so you've got a lot of thermal growth, a loop is probably the way to go. It really depends on the situation, but I'd say using the geometry and the inherent flexibility of the pipe is high on the list. But we can also use expansion joints, spring cans, and a number of other things to control the thermal growth, or to direct movement in a way that doesn't adversely affect a piece of equipment or a pump or a tank.
Okay. The next question that came in is, how big of an issue is water hammering in regards to pipe stress? And is that more of a function of poor controls or a bad install?
There's a lot of different things that can cause water hammer. I won't go into some of the, a lot of the different causes, because it can be certain pump startup situations, valve slamming situations. And you don't really think of it as water hammer, but one of the things like a pressure relief valve going off, that will cause a kind of a shock to the system. Now, The water hammer itself, it can be a big deal. It depends on what causes it and kind of the geometry of the system, because what you're going to have is a shock wave that travels down the pipe. So depending on how the system's put together, you know, as a shock wave makes a turn or hits an elbow, that you can get a considerable amount of force. So I would say, you know, any system where we think there's a potential for water hammer, we'll kind of take a look at that, and we can kind of design for that sort of thing, so that if a hammer happens, the piping is kind of set up to absorb that shock wave. But it's one of those where there's just a number of different things that can cause it. It can be severe. I've heard of and seen instances where a water hammer has taken flanges apart or broken a piece of pipe. So I mean, yeah, some of them is something you can design out, and some is just unforeseen situations. So when we think there might be that potential, we will try to design to kind of absorb that shock, or we would work with process to, you know, get a soft close valve, or something to alleviate that pressure wave when a pump starts or stops. Kind of, you know, the obvious occurrences, sources of that.
Okay. The next question is, what is the most common issue you see in facilities related to pipe stress?
Well, every facility is going to be a little different, but the thing I think that we consistently see is, especially in older facilities, is where you have a pump. Can be any piece of rotating equipment, but it's most typically going to be a pump, and either the suction or discharge, one direction or more, will have a high loading. And, you know, maybe it's not a high enough loading that you see an immediate issue with the pump, but most of the facilities we go into, we will find that the loading on that pump is higher than the API allowable or the Hydraulic Institute allowables. Centrifugal pumps tend to fall into a couple of categories, an API type or a Hydraulic Institute type. But they look at the allowables and the nozzle loadings pretty similarly. And I would have to say that's the one thing we consistently see in almost every facility, is some amount of overstress in the rotating equipment.
Okay. Next question is, how do the fluids categories correspond to level of care in the code?
Yeah, we always get a question about this. So category D, due to its nature, you know, it's lower pressure, it's lower temperature. So I wouldn't say there's any less level of care. We're going to look at that piping the same. We're going to do the same analysis on the piping, but you know, welds can be visually inspected. You can braze or solder joints. You can use miter bends more easily. The valving doesn't have to be quite as high a quality, and you can do a service leak test instead of a hydrostatic leak test. Now, category M, on the other hand, you've got much more stringent weld inspection requirements. Soldered and brazed joints are completely prohibited. Socket welded joints are limited to 2 inches or less. Much stricter requirements on how you use a miter bend. You have to have not only a full hydrostatic leak test, but what they call a sensitive leak test, where you're going to bubble test some of these flange and weld connections. And you're going to take special care to minimize impact or vibration in the system. So it's just the inspection and the restrictions are much more stringent for that category M piping than for category B.
Okay, we just have a couple left here. How big of a concern are seismic loads in an area with little seismic activity?
Well, you know, every pipe stress analysis is going to conduct wind and seismic loading. Wind if it's outside, seismic always, because you know the code was going to require it. But what we typically see is that the areas where there's infrequent or very little seismic activity tends to have a lower seismic load. There's tables that they're published so that for any spot in the U.S. we can figure what the seismic loading is going to be on the pipe, and usually these areas have a relatively low seismic load, like maybe 5% of gravity in the lateral, as opposed to California or Puerto Rico that has maybe a high seismic loading. It can be up to 20-25% of gravity loading in the lateral. Typically, if the piping is outside, the wind load is actually going to be quite a bit higher, and that's going to be what we really have to worry about. But it's if you're in an area that doesn't have a lot of seismic activity, it's usually not a big deal. A minor amount of change to the piping can make it pretty resilient to those relatively low loads, but we'll check it every time.
Okay, and the last question we have at the moment is, how is pipe fatigue checked against code?
Okay, so that's a good one. Now, remember we were talking about Category M a few minutes ago. Category M will, in the code, it asks you to minimize shock and minimize vibration, but it really doesn't talk about fatigue. Now, if you are a high pressure piping, then there's specific requirements for fatigue. And basically, you've got some fatigue limits built into the thermal stress. There's a factor included, and as you move past about 7,000 cycles, you'll see that factor start to drop below 1 to kind of account for basic operating cycles. But if you've got a situation where it's an external source, or the system is going to be starting and stopping a lot more than 7,000 times, what the code does is direct you to Section 8, Division 2 or Division 3. There's specific processes there for looking at fatigue, for evaluating fatigue in pressure vessels, and these can be applied to the piping. So if you've got a lot of movement and you think that fatigue is going to be an issue, and like I said, on those high pressure pipes, it's a requirement that you look at it, because again, pressure cycles in that 6,000 psi range can be pretty significant. But again, beyond just a basic allowance in the thermal stress equations for cycling, if you feel like there's a big problem, then you move into that Section 8, Division 2 or Division 3, those specific rules, and we'll typically look at it with finite element analysis at that point to really get a good idea of what's going on and what the fatigue is doing to the pipe.
All right, well, at the moment, that is the last of our questions. So I don't know if either you or Brandon had a wrap up. And if not, I can certainly do that.
Yeah, I think we've got one more slide here. So for more information on pipe stress, you should have a link for the Matrix on Manufacturing. I've got a couple of articles out there. I start at the basics and I kind of slowly work my way up. PDH certificates will be mailed by this Friday, September 18th. Watch your email and our social media for the November webinar, Risk Management, hosted by Carl Bowman. I think it's going to be a really good one. I'm excited for it. And make sure to subscribe to our YouTube channel. Should be some bi-weekly videos out there for you guys to take a look at.
All right, very good. Well, thank you, Chris. Thank you, Brandon, for your time and the information. And thanks to all our attendees today. And we will be having future webinars. We'd love to have you join us again. Thank you very much.